So far, when we discussed hydrocarbons, we looked at alkanes, alkenes, and alkynes. The last category of hydrocarbons that we'll look at are aromatic compounds. Aromatic compounds come from the term aromatic, which indicates that they are fragrant, which they often are. Sometimes that's a good thing, sometimes it's a not so good thing. So they can be pretty stinky, or they can smell great, depending on the particular compound that you're working with. So aromatics are classified according to them containing a benzene ring. So this right here is a benzene. Notice that there are 6 carbons connected together in a cycle, and there are 3 double bonds in that ring. So you can draw that in a couple of different ways. So you could draw the double bonds in this direction, or you can move that 1 carbon across and draw them in that direction. And these are equivalent. They both mean benzene. These are completely equivalent structures. Now, the interesting thing about benzene is that these double bonds are not centered on these specific carbons. What's really happening is that there are 6 electrons that are being distributed across all 6 carbons at the same time. So sometimes that is represented by drawing a circle inside the benzene structure to indicate that these 6 electrons are delocalized, which means they are distributed across all 6 carbons. So these 3 depictions are completely equivalent. You can draw them any of these 3 ways. You could also see any of these versions in textbooks or any chemistry that you're reading. So be able to recognize any of these. They're all benzene. They're all equally correct. One thing to keep in mind, and this is a very, very common point of confusion, is that benzene is not the same as cyclohexane. So benzene has these double bonds inside of it. Cyclohexane does not. And sometimes students confuse these two. They are not equivalent. And they have different names for a reason. They are completely different compounds that behave very differently. So the one on the left is benzene, the one on the right is cyclohexane. And if you're ever not sure, and if that distinction is not completely clear, draw it in the expanded format. So I'm going to draw these in the expanded structural formula format. I'll start with benzene. I see there are 6 carbons all connected in a cycle. And then notice that these 2 have a double bond between them. So I'll write that down here. Then we skip one, and the next one is a double bond. That was not a straight line. And then we'll skip that one and go to the 3rd double bond. Notice that each of these carbons contains 3 bonds, which means that each one only needs 1 hydrogen to complete its octet. So benzene in its expanded format is going to look like this. And if you were to convert that into the molecular formula, no, I did not write that very well. There are 6 carbons and 6 hydrogens, so that becomes C6H6. Let's take a look at cyclohexane. We also have 6 carbons that are connected in a cycle. But notice that now each carbon has only 2 bonds, which means that each carbon needs to have 2 hydrogens to complete its octet. So cyclohexane is going to have 2 hydrogens all around the ring. And that will give us a very different molecular formula. We still have 6 carbons, so C6, but now we have 12 hydrogens. So this molecular formula is C6H12. Very different structures, different types of different numbers of hydrogens. And notice that Benzene is going to have a trigonal planar geometry, whereas cyclohexane is going to be tetrahedral. So this is trigonal planar all around, and this carbon is tetrahedral. This is going to give them completely different shapes. Benzene will be flat and planar. It would fit on the surface of a sheet. Cyclohexane would not. Very, very different structure, which means they behave very differently. So be careful with those. Make sure you're not confusing them. They look kind of similar in the line angle formula, but cyclohexane doesn't have the double bonds. There are a few common aromatics. So the one on the left, it has two benzene rings fused together. This is naphthalene, and this is what gives mothballs their distinct scent. Hence the term aromatic, right? They all are smelly in their different ways. The one on the right is cinnamaldehyde, which, as the name suggests, is found in cinnamon. So this one smells really nice. Very nice cinnamon scent. The one on the bottom left is benzaldehyde. This is found in almonds or almond oil. And, well, it smells like almonds. So it's commonly used in flavors and fragrances as a flavoring agent. The thing to watch out for in terms of reactivity is that aromatics look like alkenes, but they do not behave like alkenes. One thing I wanted to point out is that any compound that contains a benzene is considered aromatic. And it doesn't matter how many benzenes you have, as long as there is a benzene present somewhere, the compound is aromatic. So there are lots of aromatic compounds out there. Even if you have a really huge molecule and it has a benzene or a few benzenes, it's considered an aromatic compound. Okay, in terms of reactivity, and this is really important, benzene does not react like alkenes. So it looks like a bunch of double bonds, that's fine. They do not react like alkenes. So benzene or aromatics are really going to do combustion reactions. So benzene does combustion, and that is it. That is the only aromatic reaction that you're going to see in a GOB course, which is General Organic and Biochemistry, which is really designed for health sciences. You will not see benzene reactions in this course. So if you see it anywhere in a molecule, just leave it alone. It's not going to do anything. Now that we know what aromatic compounds are, let's name them. And you'll see that this is going to be similar to cycloalkanes and cycloalkenes. Anytime you have a cyclic compound, there will be similar rules. So just like the ones we saw before, if a benzene has one substituent, there is no numbering needed, because it's understood that you're going to give the carbon with a substituent carbon 1, and then it becomes redundant, right? If it's always 1, there's really no point in indicating that. Benzene is going to be the parent name, so that's the structure of benzene, which means the parent is benzene. And then we'll just list the substituent name. I notice that the substituent has 2 carbons, so that is an ethyl group. And then we're going to put that together. We'll list the substituent name first, and then the parent name, and that becomes ethyl benzene. Fairly straightforward. If there are 2 or more substituents, then we're going to number the carbons to give all the substituents the lowest possible number. And just like cycloalkanes, if we need to break a tie, we will use the alphabetical order of the substituents. Very, very similar rules. Let's try an example. All right, so I see the parent will definitely be benzene. That's the cyclic compound. And then I can number this in a few different ways. So I could give this substituent carbon 1 and then continue in a clockwise direction. Or I could give this substituent carbon 1 and then continue in a counterclockwise direction. And then I have to decide which version I'm going to use. I see that in either option, the substituents will be in carbons 1 and 3. So since I have a tie, I'm going to use the alphabetical order of the substituents to break that tie. Well, this is bromo, and this is chloro. And bromo is first alphabetically, so I'm going to use the version that gives bromo the lower possible number and not the one that gives chloro the lowest number. After that, it's pretty much the same thing we've been doing before. The parent here is benzene, and then I have 1 bromo and 3 chloro, and I'll list those in alphabetical order. So bromo is listed first because it's first alphabetically. Then we have 3 chloro, and then the parent name gets tacked on at the end. And that becomes 1 bromo, 3 chloro, benzene. Let's try another one. All right, so similar type of system. I see that I have 2 substituents. The parent name will definitely be benzene. And then I have to decide the numbering order. So I could give chlorocarbon 1 and then go clockwise. Or I could give, and I could have gone counterclockwise as well because it would end up being the exact same numbering system. It's completely symmetric. Alternatively, I could give fluorocarbon 1 and then go either clockwise or counterclockwise. It will end up being the same number. Okay, so in either case, one substituent is on carbon 1, the other one is on carbon 4. So I'm going to use alphabetical order to break the tie. And chloro is first alphabetically, so I'm going to give chlorocarbon 1, not fluoro. Oh, that should have been an eraser. There we go. Okay, so the parent name is benzene. This substituent is 4 fluoro. This one is 1 chloro. And then I'm going to list that in alphabetical order, and chloro gets listed first. And that becomes 1 chloro, 4 fluoro, benzene. And that's it for that one. There are 4 special aromatic groups that you will need to know. And whenever you encounter one of these, it becomes the parent name. So if you see a benzene with an OH group attached to it, that is called phenol or phenol. So make sure you know that name. You could see instead of an OH, there could be an NH2 group. That is called aniline. So if you see a compound that has that as the backbone with some other substituents on it, then you will call it aniline. If instead there is an aldehyde, in subsequent videos we'll go through all of these functional groups so you'll see what an aldehyde looks like. This is an aldehyde, but we'll talk about that in more detail later. If it's attached to an aromatic group, then we call it benzaldehyde. That's a compound that you saw earlier, the one that smells like almonds. And if instead of having an aldehyde, there was an oxygen in between that carbon and hydrogen, then that is benzoic acid. So if any of these compounds are present in a structure, they are the parent name. And we'll try a few examples of these so you can see how that works. In any case, if you have one of these, the carbons that is directly attached to the functional group is carbon 1. So in phenol, the carbon that's attached to the OH is carbon 1. In aniline, the carbon that's attached to NH2 is carbon 1. In benzaldehyde and benzoic acid, we have to be a bit careful because the aromatic carbon attached to the functional group is carbon 1. Sometimes students get that confused and they put this one as carbon 1. That's not what you want to do. You want to make sure it's the one that is on the aromatic ring. Okay, so let's try a few examples where one of these are the parent name. I can't get this thing to expand and be in a proper orientation. Okay, lots of substituents there. Okay, right away I see that there is a benzaldehyde, right? So the parent name is going to be benzaldehyde. I'll leave that highlighted. And because the parent is benzaldehyde, we're prioritizing the carbon that is attached to the aldehyde. So now we have to decide whether we're going to number counterclockwise or clockwise. And in either case, it looks like the substituent will be on carbons 3 and 5. So now we're a bit stuck, which means we're going to use the alphabetical order of substituents to break that tie. And I see in this scenario, I have a 5-methyl. There's one carbon, so methyl. This is isopropyl. So in that case, I would have a 3-isopropyl. So we're going to go by alphabetical order to break the tie. For 5-methyl, it's straightforward. We're going to use M. In isopropyl, we have to be careful because iso is the only prefix that actually is considered when alphabetizing. So we are alphabetizing by I, not by P. So it looks like isopropyl will be listed first. So that's actually the correct numbering system. We want to keep this version, not this version. And now that we have that, we can go ahead and list our substituents in alphabetical order and put all of that together. So in this case, we will have 3-isopropyl, 5-methyl benzaldehyde. And that is the full name of that particular compound. Let's try another one. The first thing I'm going to do is identify what the parent name is. And it looks like we have an aniline present. So the parent name will be aniline. And then we'll go through and number these. That's definitely carbon 1. And then I have to decide whether to go clockwise or counterclockwise. If I go clockwise, the next substituent is on carbon 2. Whereas if I went counterclockwise, the next substituent would be on carbon 4. So I would rather give the next substituent the lowest possible number. So here we'll use this numbering system. We don't have to use alphabetical order because we don't need to break a tie. If we go clockwise, the next substituent has the lowest possible number. Then we'll go through and name these substituents. This one is 2-methyl. And this one is 4-tert-butyl. And again, here we have to be careful. So for methyl, it's straightforward. We're alphabetizing by M. In tert-butyl, keep in mind that tert is not considered when alphabetizing. So here we're actually alphabetizing by B, not by T. So tert-butyl will be listed first in the full name. So that becomes 4-tert-butyl, 2-methyl aniline. Let's try one more. Okay, so it looks like we have benzoic acid as the parent. Which means this will be carbon 1. And then I have to decide whether to go clockwise or counterclockwise. If I go clockwise, the next substituent is on carbon 4. If I go counterclockwise, the first substituent is on carbon 3. So I would prefer to give it the lowest possible number, so we're going to go in a counterclockwise direction. And then we need to identify our substituents. This is 4-fluoro. And this one is 3-sec-butyl. If you don't remember these prefixes, just keep in mind that this carbon right here is attached to 2 carbons, and we're not counting the parent chain in that. So this would be a secondary carbon, hence the prefix sec. And when it comes to alphabetizing the substituents, fluoro will go by F, of course, and sec-butyl, the sec prefix is not considered when alphabetizing, so this will be alphabetized by B, which means I'm going to list the sec-butyl substituent first in the final name. And that becomes 3-sec-butyl, 4-fluoro benzoic acid. And that's the compound name. That is it for hydrocarbons.